Welcome to Calculus.
We've always been good at math. How hard could calculus be?
On this episode, Stevenson will demonstrate
Have you ever wondered why this would be considered a maximum? Well, we can actually use derivatives to help explain this phenomenon. So naturally, we're going to use our calculus skills to level up a concept that we thought we knew. So how come at point C we can say this is a maximum? Well, look at the derivative before and after it. So this goes into the idea of increasing and decreasing. So if you look at to the left of this point, you see how the function is increasing? So that means that its derivative is positive. What happens to the right of this? Notice it's decreasing. Well, that means the derivative is negative. So there's going to be a local maximum at this point because the derivative changes sign from positive to negative. Let's look at the next one. Why is f of c a local minimum? We can see graphically it is, but why does it work? To the left of c, we can see the function is decreasing. That means the derivative is negative. To the right of the point, we can see the function is increasing. That means the derivative is positive. So why is this a local max? F of c is a local maximum because the derivative of f, or f prime, changes from negative to positive. Is it possible to have no extrema? Yes, we've seen that before. But how do derivatives come into play? Well, let's look at this example. At f of c, there is no local extrema. Now, why is that? Well, let's look to the left. Notice the graph is increasing. That means the derivative is positive. At c, it's paused for a moment, but then to the right of it, notice the graph is still increasing. So again, my derivative is positive. So why is there no local extrema here? Well, what didn't change? There was no change in sign of my derivative. In other words, there was no change in behavior of my graph. So I'm going to say that f of x has no local extrema here because the derivative did not change sign. Let's look at endpoints. The first derivative test can also be applied to endpoints. So again, we're going to have our functions f of x. So let's look at this point at c. Endpoints can also be extremas. So again, we can use the derivative to help us evaluate that. So let's look at this first one. Why is f of c considered a local max? It's a left endpoint. Well, what happens to the right of it? What do you notice about the derivative here? Notice the graph is decreasing, therefore the derivative is negative. What this means is f of c is a local max because to the right of it, the derivative is negative. Let's look at the next one. Why is this left endpoint considered a minimum? Well, again, look to the right of that point. What is the graph doing? It's increasing. That means its derivative is positive. So, the left endpoint is considered a minimum when the behavior to the right of it is increasing, or in other words, the derivative is positive. Now let's look at a right-hand endpoint. So this is considered a local minimum because if we look to the left of it, we can see the function is decreasing. So in other words, its derivative is negative. Lastly, in this function here, at this right-hand endpoint, this would be considered a local maximum because if we look to the left of it, we can see the function's behavior is increasing. In other words, the derivative is positive.